This video will present a really interesting technique to improve your knowledge distillation pipelines. Generally, with knowledge distillation, we want to have a lower capacity student network that has a faster inference time and reduced memory costs. So we're going to do this by transferring the knowledge from a higher capacity teacher network into the student network. And this is done by having the teacher network produce a new class label distribution to train the student network. So instead of having the student network trained on this one hot label encoding, where you have a 1 in the place of the label of the image, say, and a 0 everywhere else, you would have this kind of soft distribution of the different probabilities for each class provided by the teacher network. Knowledge distillation has been really popular lately with models like Distilled from Hugging Face, distilling the large BERT transformer model into a smaller model that has faster inference and less memory requirements. And it's also been used for state-of-the-art gains like self-training with Noisy Student from Google, which has reached a new EfficientNet classification state-of-the-art by using a novel approach to knowledge distillation. This teaching assistant approach is going to introduce intermediate teaching assistants between the teacher and student networks to improve the knowledge distillation pipeline. The high-level idea of the teaching assistant knowledge distillation, abbreviated as TAKD, is that if the teacher's network is too high capacity and too complex, the student network won't be able to learn from the label distribution. So the idea is to introduce intermediate teaching assistants in between the teacher and the student to facilitate the transfer of the teacher network's knowledge to the student network. Before we dive into the details of this paper, let's quickly recap the idea of distillation. So the high-level idea is that we're adding these soft labels from the teacher network in order to structure the loss function for our student network, and this is the way in which we're distilling the knowledge from the teacher network in this form to the student network. So originally the loss function is calculated by comparing the class predictions with the one-hot encoded class vectors from the original label dataset. So now the way that we're constructing this new loss function from the teacher network is we're going to smoothen out the distribution by adding in this temperature to the softmax input. So the way the softmax function works is it takes in these logits, a sub s or a sub t from the teacher, and it's going to basically normalize them such that they sum to 1. And the way that they're going to do this in distillation is they're going to smoothen it out with this temperature constant value such that the distribution over the class labels isn't too skewed towards the correct class label. So usually this would be, say, 0.98 or 0.99, something like that for a well-trained classifier. So the idea of adding temperature is that you smoothen out the class label and make it so there's more information contained in this distribution for the student network. So in the end of adding this new loss function, lambda times L sub knowledge distillation, or KD, we introduce these two new hyperparameters. So we have the temperature hyperparameter, which is how we're softening out the teacher's prediction over the class labels, and then we also have the lambda hyperparameter, which is the weighting between the original loss function with the one-hot encoded labels and the knowledge distillation loss. The core idea of this paper, introducing teaching assistants in between the teacher and the student in the knowledge distillation pipeline, is that you have to have some kind of metric of capacity scaling or measuring the complexity between the teacher and the student network to introduce intermediately complex networks. So in this paper, they have two different kinds of networks explored: convolutional neural networks and ResNets. So in the convolutional networks, the complexity is a measure of how many convolutional layers. So say the teacher has 10 convolutional layers, the TA has 6, and the student has 2. In the case of the ResNets, it's a similar idea, but instead of just convolutional layers, you're looking at these ResNet blocks. So you have 34 ResNet blocks compared to 8 ResNet blocks. So the idea of measuring capacity scales and looking at these kinds of family architectures is something that we're going to look further into this presentation in the context of a criticism on the study, which shows that if you're just looking at the width, say having 16 layers for the teacher, TA, and student, but you're just varying the width of the filters, then this doesn't work as well. And also looking at, say, compound scaling in EfficientNets, where you have another kind of way of measuring and scaling up the capacity, complexity of the intermediate networks from teacher, TA, and student. Some of the key questions of this research paper is, what is the optimal TA size for the highest performance gain? So say you have a 10-layer convolutional network as the teacher and a 2-layer for the student. How many layers should the TA have? Should it have 4, 6, or 8? The second question is, if one TA improves the distillation result, why not also train this TA with another distilled TA? So say going from a 10-layer teacher to a 6-layer TA to a 4-layer TA down to the 2-layer student. Then the third question is, would a TA trained from scratch be as effective as our approach? So basically saying, is it necessary to distill the teacher into the TA and then distill the TA into the student? Or is it just that only a 6-layer convolutional network is effective for, say, distillation into the 2-layer student network, and you even need to have this intermediate step of the teacher distilling to the TA? The first table presented in the study demonstrates the phenomenon that as the teacher increases its size and its own accuracy, it doesn't really improve its ability to distill its knowledge into the student. So we see as the teacher goes from 4 layers, 6 layers, 8 layers to 10, the testing accuracy of the teacher is increasing, but the ability of the student network to be, the accuracy of the student network once this teacher is distilled into it is actually decreasing once it gets to 6 layers. And then a similar phenomenon is found in the CFAR 100 dataset, except for at 8 layers it degrades. This table is showing the performance gains of the distilled student compared to being trained from scratch, in each case of going from a 10-layer teacher network into the student networks of the different sizes. So in this case, in the CFAR 10 dataset and the CFAR 100, we see the biggest performance gain in the 4-layer student network when it's distilled compared to training the 4-layer student network from scratch. In the paper, the authors describe 3 factors that are impacting this phenomenon. The first is that the teacher's performance increases, so it provides better supervision for the student by being a more accurate predictor. So this idea is that as the teacher gets better, it should be a better, have a better distribution for the learning of the student. However, contradicting this is in the third point. The teacher's certainty about data increases, thus making its logits, soft targets, less soft. This weakens the knowledge transfer, which is done via matching the soft targets. So as the teacher gets more accurate, essentially what it's doing is it's getting better at matching those one-hot class label vectors. So for example, if you have a teacher that has a very, very low loss, say 0.0001, something like that, its prediction on that class label is probably like 0.99, and then it assigns almost no probability to all the other classes. So as it gets more certain about the data, because this is kind of what you're training it to do as you give it a higher accuracy, it has a less soft target distribution. So it gives you less information about the other classes, which is kind of the whole idea of knowledge distillation. So maybe this could be alleviated with the tuning of that temperature hyperparameter, but it's definitely a conflicting factor impacting this phenomenon. The second is that the teacher is becoming so complex that the student doesn't have the sufficient capacity or mechanics to mimic the teacher's behavior despite receiving hints. So the idea is that even though the teacher produces this distribution, a 2-layer convolutional network, say, just can't possibly replicate the performance of a 10-layer network. So more compactly, the factors describing this phenomenon are that as the teacher performance increases, it should have better supervision for the student. But the teacher's certainty about the predictions means less soft logits, and this is because you're teaching the student to mimic these kinds of class distributions. So if you have something like really high accuracy and low loss, you're essentially producing this kind of a label distribution. And the third factor is that the teacher is just too complex for the student to possibly mimic. This prepares us to view the first result table introducing the teaching assistant in between the teacher and the student in the knowledge distillation pipeline. So in the CNN case, we're looking at having a 10-layer teacher network to a 2-layer student network and having a 4-layer teaching assistant in between. So with no knowledge distillation, just training a 2-layer student network or 2-layer convolutional neural network, we achieve about 70.16% accuracy on CFAR 10. Then with the baseline knowledge distillation going directly from 10 to 2, we have 72.57, and then going from 10 to 4 to 2, we have almost a 1% improvement at 73.51, and then we see a similar phenomenon in the ResNet when we're going from an 110-layer teacher ResNet in between to a 20-layer ResNet and then to an 8-layer student ResNet. We see a similar phenomenon where the teaching assistant knowledge distillation is always improving over the baseline knowledge distillation directly from teacher to student, as well as not using knowledge distillation at all, just training the student network from scratch. The previous results table uses 4 layers as the teaching assistant for the convolutional neural network and 20 layers as the teaching assistant for the ResNet. These tables show the search for the TA and the different results achieved across different layer sizes for the TAs. So interestingly, you see this kind of like optimal layer size at 4 layers of the convolutional network having a very significant improvement over 8 layers for the teaching assistant, and then a similar phenomenon shown in the ResNets. Also interestingly, the authors find an interesting heuristic for finding the TA size that complements the table shown previously. So these charts are showing the accuracy achieved when you train each of these networks from scratch. So if you train a 2-layer convolutional network from scratch, it achieves about 70%, whereas the 10-layer network achieves 85%. So interestingly, they show that the mean accuracy of the overall plot is around the same as the TA size chosen for each of these studies. So you see the 4 network size in the CNN, and you see around the 20 to 14 in the CFAR 10 and CFAR 100 for the ResNets. Further investigation into this shows the accuracy improvement compared to training the teacher network for 5 epochs, 10 epochs, 15 epochs, and 100 epochs to show the correlation between teacher accuracy and then the resulting student accuracy. This plot shows the differences between the baseline training the models from scratch and then the effectiveness of distilling the teacher into the TA and then the TA into the student. So the blue plots are just where you train the TA from scratch and then distill the TA into the student, and the red bars are where you distill the teacher into the TA and then TA into the student. Another interesting area of exploration for this is how many paths can the TA have before it reaches its student network. So this is a study showing all the different paths it can take from the 10-layer teacher network down to the 2-layer student network. So most interestingly, the best result is achieved by going directly from 10 to 8 to 6 to 4 to 2 at 45.14% compared to not having any knowledge distillation going to 41.09% and going directly from 10 to 2 at 42.56. So also interestingly is the results of these three pathways, 10 to 4 to 2, 10 to 6 to 2, 10 to 8 to 2, as well as all of the different combinations you can have. So probably the most interesting takeaway from this is that the best result is achieved by going through every intermediate step in order to get from teacher to student in the TA pathway. So it's also interesting to think about, maybe you could add, say, 9 layers, 8, 7, 5, and 3 to further improve this. In addition to a very rigorous mathematical analysis justifying knowledge distillation, they also show the results of adding the TA in the perspective of the loss landscape around the local minima. So you can see in both cases in the CNN and the ResNet, the local minimum is a lot smoother around, the area around the local minima is a lot smoother in the TA knowledge distillation case compared to the baseline knowledge distillation and then not having any knowledge distillation at all. This paper on the efficacy of knowledge distillation provides a criticism of this approach. So in this study, shown in this paragraph of their study, they're comparing the results of the TA knowledge distillation pipeline when they're using the wide ResNet and they're varying the width of the filters in the wide ResNet. So in this case, they don't find a better result by having this intermediate distillation between the wide ResNet 16.3 to the wide ResNet 16.1, which are different ways of having this kind of family of architectures, family of complexity, and scaling up the complexity, in this case looking at the width of the networks. EfficientNet has another really interesting way of looking at the complexity scaling of these convolutional neural networks. So in this case, they introduced something called compound scaling to scale up their networks from the baseline up to more complex models. So we saw how depth scaling is effective, shown by this study, by having, say, the 10-layer convolutional network distilled into the 6-layer TA into the 2-layer student network, and then we've seen the criticism that explored width scaling not being as successful. So it's definitely interesting to think about these kinds of compound scaling, the families of architectures. So in cases like the self-training with noisy student, they are comparing their family of architectures by using this kind of compound scaling rule to trade off depth, width, and input resolution. So in the paper, self-training with noisy student improves ImageNet classification, which is set this new state-of-the-art in ImageNet accuracy. They also kind of use this teaching assistant pipeline. So in this case, they're going from a family of EfficientNet models. So they don't go directly from, say, EfficientNet B0 up to EfficientNet B7, or in the more advanced case where they go B7, L0, L1, L2, L2. They don't go directly from the lowest capacity up to the highest capacity. So it's definitely interesting to observe this trend of having these intermediate teaching assistants, which is also persistent in this study as well. Furthermore, the code for this paper using teaching assistants to improve knowledge distillation has been open sourced and implemented on GitHub. You can come to this repository if you're interested in checking this out for yourself and getting started with knowledge distillation. Thanks for watching this presentation on knowledge distillation with teaching assistants, having these intermediate networks in between the teacher and the student in order to improve the pipeline. This is also a similar idea to what's presented in the new self-training with noisy student, where you go from B7 to L0, L1, L2, and L2 instead of going directly from B7 to L2. If you do try to implement this, please share your experience. Thanks for watching this video, and please subscribe to Henry AI Labs for more deep learning and AI videos.